Hello, everybody, and welcome to Unit 8, all about acids and bases. So before we even get into talking more about acids and bases, you'll notice this thing that's bold and center right in the middle on the top of the page, right? And it says acids and bases does not mean that something is corrosive. I think that is a misconception that a lot of the general public has. I always remember this scenario when I went to an estate sale, and for some reason, this guy that, they were selling the contents of his house. He had all these bottles of just like chemicals. And I don't really know why. Somebody said he dabbled in chemistry in his spare time, which is a very weird thing to dabble in. But he had all of these bottles of stuff. And there was a bottle there, and I don't remember what it was. I feel like maybe it was like lactic acid or something like that. And this other guy was shopping across from me looking at the bottles, and he sees that it's some acid, and he goes, "Oh, that's an acid. You better be careful." And I was just like, yeah, I don't really like to engage with people, especially about chemistry, because I tend to get a little bit, the teacher comes out, right? So, but I was like, oh, what a misconception. Just because something is an acid, that doesn't mean it's bad for you, because we need acids and bases all of the time. And there's acids and bases even in your body that are crucial to a lot of different things. So just wanted to get that out of the way. Just because something is acidic or basic does not mean that it is necessarily corrosive. In this video, we're actually going to do quite a bit. I'm planning on going to page 7. Hopefully it doesn't take that long, because there's not a lot of writing on these pages, and there's really not a lot of work to be done. So the only equation that we are going to do is actually relatively simple. So let's talk about some of the properties of both acids and bases. So you'll see here that the first thing actually talks about taste, which is kind of weird. But they do have specific tastes to them. So aqueous solutions of acids tend to taste very sour. And anytime you have a lemon, right? A lemon has a high, or any type of citrus fruit, has a relatively high concentration of citric acid. And citric acid is a good donator of protons. If you remember back to Unit 4, we're going to talk about again in this video, what makes an acid an acid. One of the definitions is that it donates protons. So when you consume something that donates protons, it tends to feel very sour. And actually, they coat Sour Patch Kids with citric acid. So if you have a very high concentration of hydrogen ions on your tongue, you get that sour sensation. Whereas aqueous solutions of bases tend to taste very bitter. And both don't taste very good, right? We tend to like things with a relatively neutral pH because a lot of things have water in it. So that makes sense. Some acids react with active metals and they produce hydrogen gas. So this is an example of a single replacement reaction, hydrogen gas. And actually, this would be an example of a redox reaction as well. If you consider hydrochloric acid reacting with sodium, if sodium in those reactant side has an oxidation number of 0, on the product side, if it bonds to sodium chloride, it has an oxidation number of positive 1. So that is considered a redox reaction or a single replacement reaction. And acids also will conduct electricity. Acids and bases will conduct electricity. So I'm going to write this for both of them here. Conduct electricity, conduct electricity. And depending on whether or not something is a strong acid or a weak acid, or a strong base or a weak base, depends on how much electricity it will conduct, which we also talked about a little bit in Unit 4. So you're going to start to see that Unit 8 kind of starts to bring together a lot of what we started to talk about in Unit 4, and it also is going to bring equilibrium into this as well. So we're going to start making some connections there. I did miss on the basis side, dilute aqueous solutions of bases tend to feel very slippery. So something that's basic is bleach, for example. If you spill bleach on your hands, you'll start to feel your hands are slippery. And the reason for that, and it's actually kind of nasty, but this is what I was told from the man that I student taught with back in the day, But the reason why your hands feel slippery is because the bases start to actually disintegrate your skin in a sense. So you're feeling like your skin between your skin. This is what he said. So I don't know how accurate that is, but I trust him. He was a very smart man. I'm the chemistry teacher I am today because of him. So that's what he said. So that's what I'm going with. But dilute aqueous solutions of bases tend to feel very slippery. And acids will have a low pH, which you might know already, whereas bases have a very high pH. So let's take a look at the pH scale. So we'll see that anything that's from about, we'll say a 5 to a 0 is considered acidic. So all of these right here are acids. Whereas going from about, we'll say like a 9 to a 14, all of these are bases. And another word that we use instead of basic is the word alkaline. So whenever you see alkaline, that means that there is some substance in there with a relatively high pH. So like alkaline batteries, for example, tend to have a substance inside of them that has a high pH. And here's just some different things that have each of these relative pHs. So water, we know to be neutral. Pure, distilled, deionized water has a pH of 7. We'll see milk and coffee, tomatoes, a little bit acidic, but not too much. Vinegar is relatively acidic. We're actually going to do a lab where you're going to determine the pH of vinegar and determine its Ka value. That K should start to ring a bell from equilibrium. Lemons and stomach acid. So your stomach acid has a very high pH. That's why if you vomit, you feel that, you get that sensation like it's, sour. That's your stomach acid coming up. And battery acid. So you probably have heard you got to be very careful if you're jumping your car. You got to set the clips on the right side of the battery, or you got to start at a certain time. That's because if that battery acid comes out of that battery, you're in big trouble because that is a very corrosive substance. That is a corrosive acid. Battery acid is sulfuric acid, actually, which is H2SO4. Your stomach acid is hydrochloric. Lemon is citric, vinegar is acetic, and of course there's lots of other acids and bases in between. Your blood has a pH of about 8. People try to consume very alkaline diets, and I'm not sure why, because what you're going to learn later in this unit is that your body has systems in place that resist these changes to pH. If you consume an alkaline diet, that's going to do nothing, because your body is going to get whatever you consume back to the pH it needs to be. You have these things called blood buffers, and without those blood buffers, we would be dead. So there's no such thing that an alkaline diet is good for you, because your body won't let that happen. And just going through this a little bit, baking soda, you'll see soap actually has a relatively high pH. We use sodium hydroxide to make soap, or otherwise known as lye. I would like to do a lab with you guys maybe after the AP exam, but that's a fun thing to do. And bleach and drain cleaner, super, super basic or alkaline in nature. And something that's important to note about this is that this is not like a range of 1. So for example, if I compare coffee to milk, coffee is not 1 time more acidic than milk. Coffee is 10 times more acidic than milk. And this is because this particular scale is what we call a logarithmic scale, which we're going to get into in a little bit. Anyway, we talked about in Unit 4 the definition of acids and bases. So we particularly talked about the Bronsted-Lowry definition, and that's the definition that we are going to stick with right here. But in chemistry, there's lots of different ways to identify or to define an acid versus a base, and it all depends on the scenario. So you might be like, why do we need all 3 of these definitions? Well, each of these scenarios takes or has an important function for some aspect of doing chemistry. Like I said, for the AP exam, we're only going to focus on Bronsted-Lowry, which we have done before. Acids tend to donate protons to solution, whereas bases will accept those protons. So remember, this is the one that we're focusing on right here. And in these particular examples, your acids and bases will tend to form some sort of salt, and you form water. Now, when I say salt, that doesn't mean you're going to form sodium chloride. You're going to form some substance that will dissociate in water. So you'll form some ionic bond, but that ionic bond is going to dissociate. So here's a throwback to Unit 4. So it says determine which species is the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. So if I look at A, this is hydrochloric acid. So this must be our acid in this case, because if I look at the product side, I only have chloride that's left, the chloride ion. So this hydrogen was donated to water to produce the hydronium ion. Remember, we call this the hydronium ion. That might be in these notes somewhere, I'm not sure, but you're going to hear me mention the hydronium ion a lot. So this is our acid and this is our base. Water is the base because it has accepted that proton. Remember, when hydrochloric acid loses its proton, that means that it becomes more basic. So we call whatever's left over after that proton has been donated, this is what we call the conjugate base, right there. Whereas water, or this hydronium ion, is our conjugate acid. Okay, so the base, after it has accepted the proton, becomes a little bit acidic. So we call that the conjugate acid. If I were to look at this next example right here, so you can tend to identify your acids pretty easily just by looking for that hydrogen atom in the front. So if I look at this guy right here, my eye immediately goes there. I'm like, oh, that has to be an acid. And if I look, it is, because it's lost its proton in the product side. So here's my acid. Or hydroxides tend to be very basic. They accept protons very easily to make water, as we see here. So once that proton has been donated and I'm left with this cyanide ion, this is the conjugate base, whereas water is the conjugate acid. And this last one, again, my eye immediately goes right here because when I see that proton in the front, most of the time that will indicate that something is acidic, just because it's nice to see that one acidic proton in the front. So this is acetic acid. This is my acid right here. And after it has donated that proton, this becomes the conjugate base. And here, this must be my base, the oxalate ion. And this must be my conjugate acid. So we did talk about this in Unit 4. I believe I have much more concise notes on this in Unit 4. So you can always go back to that and check to see. Something that I want to note to you as well, which I think I also talked about in Unit 4, is something that's very special about water. So if we look at these two equations right here, I have hydrochloric acid reacting with water, and I form the chloride ion and the hydronium ion here. So this is the equation that we did just right up here. And we'll see that in this example, water acts as the base, because that water is accepting that proton to make the hydronium ion. In that second equation, however, we'll see water is reacting with ammonia, and instead, ammonia takes the proton away from water, right? Water acts as the acid in this case because it's donating one of its protons to ammonia. And this is important about water because water is neutral. Water has the ability to act as an acid or a base. I think I also talked about this in Unit 4. So if water accepts a proton, it acts as a base. If water loses its proton, it acts as an acid. And we say that this is what we call an amphoteric compound. This means that it has the ability to act as both an acid or a base. It just depends on what else it's reacting with. Hydrochloric acid is a strong acid, so in that case, water will act as the base, whereas ammonia is a weak base, so water will act as the acid. So just depends on the conditions that it's in, but it does have that very unique property, which is pretty cool. Let's take a look at another example of acids and bases. So we talked about Bronsted-Lowry, but it's also important for us to look up at Arrhenius too. I said before we're only going to focus on Bronsted-Lowry. I lied, because apparently we have to do Arrhenius as well. I tend to think of acids and bases as Arrhenius anyway, because when I see hydroxides, typically that means something is basic. But anyway, Arrhenius acids, what these are, if you have an Arrhenius acid, that means you have an increase in the concentration of the hydronium ion. Which is that H3O plus 1. It's water with an extra proton attached to it when dissolved in water. So if I have a substance that when it's dissolved in water, I'm making protons, or I'm making the hydronium ion, I'm increasing that concentration, that means that something is called an Arrhenius acid, which is basically what a Bronsted-Lowry acid is. It donates its protons, right? So in this case, an Arrhenius acid also donates its protons, but it donates its protons to something which generally will increase or will decrease the pH of that solution. So if I look at this example right here, I have nitric acid is reacting with water to produce the nitrate ion and the hydronium ion. Because I'm producing this hydronium ion, this concentration is increasing. We say that nitric acid is an acid. Sometimes, however, you might see reactions written this way. So I tend to like to write water in here because, I don't know, I like it myself a little bit better that way. When you do include that water, though, you have to include the hydronium ion, and that's because you know, law of conservation of mass, you have to balance the equation properly. Here, though, notice how I'm just splitting apart the hydrogen and the nitrate. I'm just showing that dissociation. This is still correct too. The only thing is that a lot of chemists or a lot of places don't like to use this hydrogen ion, because technically hydrogen ions don't exist but on their own. They're too unstable. These are going to immediately bond to water. From what I was taught, this is a little bit more stable. I like to write it out this way anyway. I don't know. I just like to. So I think you're going to see me use that one a little bit more. Anyway, Arrhenius bases, these will increase in the concentration of the hydroxide ion, which is the OH minus 1 group, when dissolved in water. So here I have sodium hydroxide, and that is dissociating into sodium ions and hydroxide ions. I actually don't know how to include water in this example. So notice here, I'm like, I like water here. And in this one, I'm like, I don't like water here. You're going to start to see the way I do these things. And hopefully you get comfortable with that as well. But notice how here I'm making hydroxide ions when this dissociates. We know sodium ions break apart from whatever they're bonded to relatively easily. So that concentration of hydroxide is going to go up quite a bit, which will signify that something is basic with a high pH. We also talked about this as well in Unit 4. And we talked about the conductivity of something. So for example, in Arrhenius's theory of acids and bases, a strong acid or base will completely dissociate in aqueous solution. And this is very important to know. So a strong acid, for example, is hydrochloric. Notice how every single hydrochloric acid particle has dissociated. Whereas if I have acetic acid, which is a weak acid, I have this guy that dissociated, but I have two acetic acid particles that are still together. And this is a huge difference between weak versus strong acids. And we're going to see that this affects quite a bit of calculations that we're going to do. So, because if we consider back to here, if Arrhenius acids increase the concentration of the hydronium ion or protons, strong acids increase the concentration of protons a heck of a lot more than weak acids do. And that's where we bring equilibrium back into this as well. Strong acids, because there are a lot of charged particles here, these are very strong electrolytes. These conduct electricity very well. Whereas my weak acids are weak electrolytes. We talked about that back in Unit 4, but it's always good to go back and talk about it again. And here's your list of strong acids and strong bases. Unfortunately, you do have to memorize those. There's no getting around it. I think the only way to memorize them is just to see them a whole heck of a lot. Like this one, you should know. This one, you should know. Usually nitric, sulfuric, and hydrochloric. Those are really the only ones you're going to see the most often. Does that mean you're not going to see the other ones? Absolutely not. But the ones that I start are definitely the most common ones that you will see in sample problems that we do. On that note, let's talk about the self-ionization of water. So why is water neutral, right? Why does water have a pH of 7, right? Well, in solution, water doesn't actually exist just as H2O molecules. We do have some sort of an equilibrium that exists. And you can see that this is in equilibrium because I have equilibrium arrows right here. 2 water molecules are in equilibrium with, I have 1 hydronium ion and 1 hydroxide ion. Okay. So there's some sort of an equilibrium that is established here. So when you have a glass of water, right, you also have some hydronium ions and you have some hydroxide ions. So if we were to write this equation out, right, 2 water molecules, which are in the liquid phase, is in equilibrium with a hydronium ion dissolved in the water and the hydroxide ion, which is dissolved in the water. So if I were to write the equilibrium expression, it would look like this, because remember, aqueous species are included in the equilibrium expression, but liquids are not. So the water molecules are not included there. And that particular equilibrium constant has a value. And that value for this equilibrium, the self-ionization of water, is 1 × 10⁻14th. And that is at 25 degrees Celsius. So if I consider, right, okay, based on that value of K, that value of K is very small, right? What does that mean? At equilibrium, we have a very high concentration of water molecules, but a very low concentration of hydronium ions and hydroxide ions. These have a low concentration. This side has a much higher concentration. I have a lot more water molecules because we could see that value of K is so small. And this, of course, is measured at 25 degrees Celsius. And something that we have to keep in mind, I'm not sure why I put this here, but we'll reference this later. We'll talk about that then. So let's go ahead and take a look at sample problem 2. So it says, determine the concentration of hydronium ions and hydroxide ions in pure water. So we want to determine what's this value and what's this value right here. So we know that Kw is equal to the concentration of hydroxide, or sorry, hydronium, times the concentration of hydroxide. And we also know Kw. Kw is equal to 1 × 10⁻14th. But if this is self-ionizing, if you consider what are these values, what are these concentrations, right? If you think back to equilibrium, these concentrations have to be the same because they're a 1-to-1 mole ratio. So I'm going to just set this equal to X times X because they have to be the same concentration. So if you solve for X just by taking the square root of this number, you get 1 × 10⁻⁷ molar, and that's of the hydronium ion and the hydroxide ion. So a neutral solution at 25 degrees Celsius will have a 1.0 times 10 to the negative 7th molar concentration of hydronium ions and a 1 times 10 to the negative 7th molar concentration of hydroxide ions. And that is why that water is neutral. And that's because they have the exact same concentration of both of those species, because an increase in hydronium is what makes an acid and an increase in hydroxide is what makes a base. So because I have an equal concentration of acids and bases, this must mean the solution is neutral. So let's take a look at each one of these right here. So it says calculate the concentration of hydronium ion and hydroxide ion at 25 degrees in the following strong acids and bases. So this one is a strong acid and this one is a strong base. And we have to remember that strong means that it completely dissociates. This makes life a lot easier with calculations. So in this video, all we're focusing on is that they completely dissociate. So let's consider, right? I have nitric acid. Nitric acid will completely dissociate into its ions. So I have hydrogen ions and I have nitrate ions. If the concentration of nitric acid is 0.15, I'm sorry, and if this nitric acid completely dissociates, that must mean that my hydrogen concentration is also 0.15 because it's a 1-to-1 mole ratio. So my concentration of hydrogen ions is 0.15. Okay, that part's the easy part. How do I find the concentration of the hydroxide ion? I have to use the fact that my Kw is equal to concentration of hydronium times my concentration of hydroxide. It does say at 25 degrees, so I can use that value of 1 times 10 to the negative 14th. So my equilibrium constant for water at 25 degrees is 1 times 10 to the negative 14th. And that's equal to 0.15 molar times X. So I'm trying to find the hydroxide ion concentration here. You solve and you'll see that this is a very small value. You get 6.7 times 10 to the negative 14th molar. So notice how much higher that hydronium ion concentration is. That's what makes nitric acid an acid. The hydroxide ion concentration is very low relative to the hydroxide. Why do I even have hydroxide in here? Because remember, we have water that is self-ionizing in the solution. Because I have nitric acid in a solution that contains water, some of those water molecules are self-ionizing and producing some hydroxide. Let's take a look at this strong base right here. So I have calcium hydroxide. Notice I'm not drawing equilibrium arrows here, and that's because this is a strong base, which means this completely dissociates. This is going to go to completion. So this is going to break up into calcium ions, and I have 2 hydroxide ions. So this makes our calculation a little bit different. So if I have a 0.010 molar concentration of calcium hydroxide, what does that mean for my hydroxide concentration? If I look at the stoichiometry, must be double the concentration because there's 2 hydroxides for every 1 calcium hydroxide. And that's my concentration of hydroxide right there. So I have to use that Kw expression again to find out, well, what's the concentration of hydronium? So let's go ahead and plug this in. 1 times 10 to the negative 14th. That's equal to X, which is what I'm trying to find, times 0.2 molar. And I get 5 times 10 to the negative 13th molar. And you could do hydronium, you could do protons. Ultimately, it doesn't matter, right? You could do H3O plus 1, you could do H plus 1. They all mean they're relatively interchangeable. There's your answer there. Not anything too difficult yet. Still want to keep going in this video a little bit. So what we're going to find is that neutral solutions, and this should be at 25 degrees. This is at 25 degrees Celsius. Neutral solutions at 25 degrees Celsius, your hydronium ion concentration will be 1 times 10 to the negative 7th. If I have an acidic solution, of course, my hydronium ion concentration will be higher than that, or it will be lower than that if it is a base. And one way, now we can kind of compare concentration. So to say, okay, if this is 25 degrees Celsius, what does that mean about the concentration of hydroxide ions, hydronium ions, whatever? There is a better way of determining how acidic or how basic something is, and that is by calculating its pH. And that's what we're going to do here. Equation looks scary, but it's not at all. I promise it's not hard. So the pH of a solution is equal to the negative log of the hydronium ion concentration. So for example, it says calculate the pH of pure water at 25 degrees. We've already established, right? If I look at a neutral solution, has a concentration of 1 times 10 to the negative 7th. So if I take the negative log of 1.0 times 10 to the negative 7th molar, I get a pH that's equal to 7. And that is why it has a pH of 7. Weird thing with sig figs, with taking a log of something. When you take the log of a number, you actually have to add a significant figure. Don't ask me why, I have no idea, but that's the rule, right? So notice how I tacked on an additional significant figure. That's why you actually have to add one. Remember, College Board doesn't care about sig figs, but when you do express pH, I would definitely do at least 1, if not 2 decimal places. And here's some mathematical relationships that involve pH. So the pH is equal to the negative log of the hydronium ion concentration. Anything with the P in the front is equal to the negative log of that thing, okay? So we can also calculate a pOH. And the pOH is basically the opposite of the pH. Nobody tends to use the pOH though, because why would you have 2 values that are kind of reverse of one another? Chemists like to sometimes express it. I don't know why. You do have to know that the pOH is the negative log of the hydroxide ion. And that the pH plus the pOH is equal to 14. And this is true at 25 degrees Celsius. And here's just a couple of other things as well. You're going to see, and I'll talk about these once we do problems together in class. Let's go ahead and look at these right here. So a 1 times 10 to the negative 3rd molar hydrochloric acid solution is prepared. What is the hydroxyl ion concentration? Notice it's not asking for the pH here. It wants to know what's the concentration of that hydroxyl group, that OH minus 1. So in this case, we're going to use the fact that Kw is equal to concentration of hydronium times concentration of hydroxide. It's not saying at 25 degrees. We can assume that it is at 25 degrees though. So my Kw will do is 1 times 10 to the negative 14th. That's equal to my hydronium ion concentration, because this is a strong acid, must be equal to this value right here. So I'm going to plug in 1 times 10 to the negative 3rd molar times X. And X in this case is equal to 1.0 times 10 to the negative 11th molar OH minus 1. We didn't bring in the negative log yet, but that's okay. We're going to do it right here. So it says calculate the pH of a 2 times 10 to the negative 3rd molar solution of hydrochloric acid. Remember, hydrochloric acid is a strong acid, and you have to recognize this, because if we were given what is the pH of a weak acid, I cannot just plug in that concentration, and that's because all of that weak acid does not dissociate. So there's a little bit more work that's involved with that. But in this case, I can, because all of this dissociates. So the concentration of hydrogen ions is equal to the concentration of the hydrochloric. So to find the pH, it's just the negative log of 2 times 10 to the negative third molar, which means I have a pH of 2.7. And there are no units for pH. It's just a numerical value, 2.7. So C says, what's the pOH and the pH of a 5 times 10 to the negative 2 molar solution of sodium hydroxide? So in this case, this is a strong base. So if this is a strong base, this must mean that my hydroxide ion concentration is equal to 5 times 10 to the negative 2 molar. So if that's the concentration of the hydroxide ion, and if I take the negative log of that number, that's going to give me the pOH. So you just have to be careful of that. So if I take the negative log of this, it's 1.30. And even if you would kind of infer, so let's say you did think that was the pH, you would be, wait a minute, that's a very low pH and it's a base, so that can't be true. That's because this is equal to the pOH. So if you were to find the pH, you would just have to take 14 minus 1.30, and you would find that your pOH is equal to 12.70, which makes a lot more sense considering this is a strong base. It should have a higher pH. In this case, we have the pH and we want to know the hydrogen ion concentration in the solution. So we're working backwards in this sense. The negative log of the hydrogen ion concentration is equal to 9.67. So holy moly, how the heck do I solve for this, right? And to bring this negative over, so log of the hydrogen ion concentration is equal to negative 9.67. And in order to cancel out that log, we have to what's known as exponentiate. Exponentiate. That's a GQ phrase right there. And we got to raise both sides of this to the power of E. I don't know if I'm wording that correctly, but we got to raise it to the power of E. So what that does is that it cancels out that log, and you're left with the hydrogen ion concentration, if you do this on the calculator, would be equal to 2.1 times 10 to the negative 10th molar. And that makes sense because this has a relatively high pH. This is a base. It should have a relatively low concentration of that hydrogen ion concentration. We're going to do lots of practice with this in class, so don't panic that you're not too comfortable with this yet. That's what we're going to do all next class. Let's get through this really quick. I know this is a long video. I'm sorry. I just wanted to get all of this done. I think all of this stuff is easy. And we get a lot of stuff crossed off the list that you need to know. So anyway, the equilibrium constant for the self-ionization of water, so Kw, we'll see that as temperature increases, right, the value of K is also increasing. So if the value of K is increasing, this must mean that my concentration of products is increasing. If I think back to equilibrium, right, the higher the value of K, the more products I have. So as K is increasing, my concentration of hydronium ions and hydroxide ions is also increasing, which I could see going down this group. So it increases with increasing temperature. So even though the concentration of hydronium ions and hydroxide ions change, when the value of K changes, they are still equal in solution. So even though the value of K is changing, because remember, the value for K, W, is equal to the concentration of the hydronium ion times the concentration of the hydroxide ion. No matter what Kw is, you just have to take the square root of that Kw, because hydronium and hydroxide are going to be the same value, the same concentration. So if you take the square root of each one of these Ks, you will get this value here. That means that the concentration of hydronium is always equal to the concentration of hydroxide. What does that mean? That even though the K is changing and even though the pH is changing, because if I take the negative log of this number, because it's technically the hydronium ion concentration. It's going to give me this. The pH is still neutral. This pH scale changes based on the temperature of that particular solution. We, however, tend to consider water at 25 degrees just because that's about room temperature, right? So you normally don't have to worry about this. You might see a question or two relating to this on your exam, but it is important to note that if the value of K is increasing with an increase in temperature, right? What does that mean about this reaction? Is this reaction endothermic or is it exothermic? This reaction must be an endothermic process. Let's think about it. So if I add heat to water, the higher the temperature, Le Chatelier's principle, the higher the temperature means I could produce more products. So in that case, when temperature goes up, my value for K is changing because my concentration of products becomes greater than the concentration of reactants. And that's super important. Even though the pH is not equal to 7, all of these are still considered neutral. And that's because the concentration of hydronium is equal to the concentration of hydroxide. And this self-ionization of water is what it's called, is an endothermic process. I know that was a lot of information. I'm sorry. But hopefully that was good for you. We're going to get some practice with this next time I see you. And otherwise, I will see you in the next video all about weak acids and bases. So I'll see you then. Bye.